Okay, welcome everyone to yet another one of our distinguished lecture series. I think this is the penultimate one, right? There's one more in 2 weeks, or maybe there's two more. I don't remember. But anyway, distinguished lecture series for the Institute for Experiential AI. I'm Usama Fayyad. I'm the director of the Institute for Experiential AI. And it is my distinct pleasure today to introduce Ron Brachman. So I can do the formal intro, but I've known Ron for a long time. In my history, when Ron was running kind of the most prestigious AI group, maybe in the world, at Bell Labs at the time, he actually tried to hire me. Issued me an offer letter to join his group. And then I got this very memorable call from Ron where he basically was saying, Usama, would love to have you join, but it looks like they're going to break up Bell Labs. So I don't know what to recommend to you. It was very interesting. And in the end, anyway, I ended up going to Microsoft Research. Ron ended up staying at AT&T for a while. But the story of Bell Labs that became AT&T, the story has another nice ending. So Bell Labs kind of went through a bad period, and at the time we were starting also Yahoo research. So in a nice twist of fate, I ended up hiring Ron to come help us build Yahoo research. And he kind of built it out of New York for a while, and then was running the whole thing towards the end of it. Before he left to go to Cornell, or did he go to DARPA after?
No,
DARPA was before, right? DARPA was after Bell Labs, where he ran programs that established some pretty interesting things, including Siri coming out of that program. Whether you consider that good or bad is a different story. But after Yahoo research, Ron was running the institute over at Cornell Tech in New York on Roosevelt Island. That's a joint institute and campus between Cornell and Technion. So pretty interesting background. The last thing I'll say about Ron, other than he went to Princeton and then he did his PhD in Harvard, is that all his early work was on very hard problems like knowledge representation. Problems that to this day still don't have good solutions. So one of those problems is common sense reasoning. I think today, especially with generative AI, if I were to make the biggest criticism I would make of those systems, and don't be fooled with the chatbots that are sitting on top of the large language models, they still don't have any reasoning capabilities. And those chatbots are still facing the same problems that have been faced for the last 60, 70 years without good solutions. So we do have today a dependence on technology that appears as a stochastic parrot to be intelligent and to do reasoning, yet it doesn't even have common sense reasoning. So with that, I'll introduce our speaker, Ron Brachman. Ron?
Osama, thank you very much. It's a great pleasure to be here with you today, those of you remotely. I do want to make one quick remark. I want to talk about what really seems to be a pretty underappreciated but critical problem in AI. Osama's already hinted about what that is, but this is not going to be a technical talk. So if you were looking for equations or matrices or experimental results, I'm really afraid you're going to be disappointed. So I hope you'll bear with me. The point when I'm finished may appear completely obvious in retrospect. That may be fine. But I kind of want to make a pitch for work to change direction a little bit, and you can think of this rather than a technical lecture as more a call to action. With that, I also want to acknowledge my co-author, longtime co-author Hector Levesque, with whom I've worked for, I hate to tell you how many years, more than 40. And a lot of what I have to say here is actually from him rather than me alone. So let's start out with a really mundane situation. So pretend it's the middle of the week, you're off of work in the afternoon for some reason, and you have to do an errand in your small town, and you, in your car, come up to a T intersection. This happens to be the T intersection at the end of my own street. I've gone through that intersection probably thousands of times. And what you want to do is go to a place that you're very familiar with. I've taken the same route. Think of yourselves as taking the same route to do this errand literally hundreds of times. And virtually every single time, you've gone the same way. And in particular, you've turned left here because of the ease of getting to the place you want to go. Now imagine under normal circumstances, you'd make a left turn. You often do that completely without thought. You know where you're going, you've done it hundreds of times, you're listening to the radio or talking to your passenger, you're just going to make the left turn. But the passenger in the seat next to you tells you, remember, it's 2:30 in the afternoon and there's an elementary school down the block. And you quickly remember what craziness it is when people are picking up their kids from elementary school, and you might decide that's not the most fruitful path to take. Or it's in the fall and you happen to notice this spectacular tree on your right, and you want to go take a look because it's not going to take you very far out of your way. Or you look to your left and you see a moving van backing out into the street with somebody waving their arms. It's kind of a familiar scenario, sort of, uh-oh, this is going to take me a long time because these are amateurs directing traffic. Or something less common, you've left the house and the ground underneath your feet has been rumbling, and you come to the intersection and look to your left and the street is buckling. Now that's pretty out there, right? But you may recall, this happened to us in New Jersey about 3 weeks ago. And no system that's trained on local data would ever have encountered a street buckling earthquake in my neighborhood. So through one of these reasons, you turn right. Could be any one of them, it could be many others. Normally you'd go left. Now the crucial thing here is you had a reason for making that turn, right? You thought of a reason quickly. You might have done a quick observation. You might have heard something on the radio. Your passenger might have said something to you. But the reason, the street buckling, the school letting out, was the direct cause of your action. You took action because of some mental computation you did. And the frequency of turns that you made in prior errands of this sort is completely irrelevant. In fact, it could be that every single time in your entire life you've ever done this errand, you've gone left, but those reasons popped up and you decided, I'm going to go right. Perfectly plausible scenario. The reasoning and the turn are not the same kind of skill you have in when you learn to drive and just manage the road, like staying in your lane, braking smoothly, avoiding going up on curbs. Very different kind of phenomenon, but I think you would agree with me that the reasoning we just went through is what you would call commonsensical. Not deep thought. I didn't pull out my computer and do a new route calculation. I didn't have to deal with the GPS because it was something that happened right away. I've taken these various routes many times, so I called to mind what it would be like to go right instead of left. And I probably did a very quick mental projection forward of what's going to happen if I turn right rather than go my usual way. But the critical thing is, it has nothing to do with statistics or frequency of how often I've made a turn in one direction or the other. Now, I would argue, and Osama sort of set the stage, that today's AI, if you will, largely dominated in deployment by large language model-based systems, certainly other machine learning-based systems like the, let's call it the quote, full self-driving unquote in my Tesla. Those systems that are deployed, generally speaking, do not have articulable reasons for what they do. They're trained on vast volumes of data, LLMs, of course, on text. My car navigation system was trained on lots of presumably sensor data of the sort that my car picks up. These things are not trained like you and I were in school on principles, explanations, or enhanced situation descriptions that let us make decisions between alternatives that have some, if you will, logical relationship to one another. And you all know well that basically statistics at heart drives deep learning. And it's great, absolutely great on things that you might consider unconscious skills in humans, like smooth braking, lane following, avoiding going up on the curb, and things like that. The interesting thing about this technology, and you may have heard this before, and it's somewhat scary as we see broader deployment, is that even the system designers do not know what the reasons are that machines do what they do, right? Here's a quote from someone basically saying, the people who trained and people who designed the system have no idea what the reasons are for the decisions that the machine makes. And in a corollary, very importantly, these machines don't have what we would call common sense. We're not the only ones to have pointed this out. I believe that Jan LeCun has spoken in the series before. He's many times said that today's AI doesn't have anywhere near the common sense of a house cat. You may be familiar with Yi-Jun Choi, a researcher at the University of Washington and the Allen Institute, a MacArthur winner. She gave a talk last year at TED. If you're interested in this, you might want to take a quick look at it, where she basically also reinforced the fact that AI systems seem shockingly stupid when it comes to mundane, average decisions of the sort that humans do. And you can see this, and you may have seen this online. I'll give you a couple of quick examples. The deployment of these systems are really fraught with inexplicable, sometimes just bizarre-looking decisions that humans would never make. And this is very worrisome. We'll say why in a moment. So, self-driving cars, for example, and I use that term loosely. I guess they self-drive when it comes to actually manipulating the steering wheel and the brakes. They're not so good when it comes to achieving broader goals. But there was a case not long ago where a Tesla saw a policeman with a stop sign depicted on a billboard and put on the brakes and came screeching to a halt. You've probably seen other examples. In San Francisco, some self-driving vehicles, not Teslas, but from Waymo and Cruise, did exactly the opposite of what commonsensical you'd like to do when you meet with an emergency vehicle. You're supposed to get out of the way, right? In a sense, everyone knows that. If you've done any driving, you've had any training, you're kind of a normal adult human being these days, you would get out of the way. These things did quite the opposite and block the way of emergency vehicles. This happens in image recognition as well. Lots of interesting cases here. Imagine you're looking in the rearview mirror of your car and you see this. Is the first thing you thought of that that's an ostrich? Well, probably not. It doesn't even resemble an ostrich in any commonsensical way, but there was a paper a few years ago that showed with a little bit of adversarial data insertion, image recognition algorithms could determine that almost everything they saw was an ostrich. Or, for example, another example, somebody showed an image recognizer, a picture of a turtle, and it very confidently said that's a rifle. Okay, language-based systems that you're all familiar with. This is an example from Alexa, but there are many, many others. A couple of years ago, a 10-year-old said to Alexa, "I'm bored, please give me a challenge to do. I want something interesting and challenging to do." And Alexa said, "Plug in a phone charger about halfway into a wall outlet, then touch a penny to the exposed prongs." I guess you could argue that's an interesting thing to do. Potentially lethal, and just not what a sane, commonsensical adult would do under any circumstances. And of course, there's lots and lots of examples, you can find them online, of other ways in which LLM-based systems go wrong. Not long ago, a couple of months ago, ChatGPT went off the deep end, started giving nonsensical responses to virtually everything that it was asked. Just in this morning's paper, there was a discussion of some deployment of AI that Facebook has done, Meta has done, and how bad the system is and how bizarre are the mistakes that it makes. So I think it's pretty well known, and again, we can find lots more examples, that AI as currently built and deployed, especially when dominated by machine learning with large data, training data sets, does not really have common sense. Now you might ask yourself, okay, well these are mundane examples and the kid probably didn't stick the penny on the phone charger anyway, so what's the big deal? And for sure, if the technology is out there for entertainment value or nothing important rides on the results, then occasional failures like these are not really an issue. Funny thing about this Facebook system that was mentioned in the Times this morning, the writer basically said, well, maybe we should think of this as a fancy emoji generating system. Now, I suspect that that's not what Mark Zuckerberg wants to hear about the multi-billion-dollar investment he's made. But if it is a weird emoji generating system, no big deal if it makes bizarre mistakes. But when we deploy AI in systems that are autonomous, our goal with self-driving cars, with interstellar rovers and space missions, with search and rescue missions that are out of radio contact and can't be teleoperated, autonomy matters, and mistakes, bizarre, inscrutable mistakes, unhuman mistakes, can really be fatal. And of course, we've heard about many examples of these, especially in the driving arena. But when we talk about human interaction with AI, I know a very large focus of the Institute here, another problem with this unpredictability is it simply undercuts trust. We learn to trust one another not because we believe each of us is perfect, but because when we make mistakes or we do things that are wrong, they're kind of within a reasonable range of rational behavior, and we can often figure out what was the reason you did that, and maybe excuse it or maybe help you improve it next time, or maybe you get declared not guilty by a jury. But nevertheless, having rational reasons for doing things is really a crucial element of trust. And as we deploy AI in more and more settings, really the trust element's really critical. Gary Marcus just the other day in the Times was talking about one of the deployed systems and basically said these things are great, they're right some of the time, but you just don't know which part of the time they're right. That's really pretty difficult for tool using or deploying autonomous systems. And as I said, our human decisions generally make sense, even if they're wrong. In fact, a colleague, I don't know if you know him, Henry Lieberman at MIT, has distinguished between two kinds of mistakes. He uses the terminology charming mistakes for things that, well, that was a goof, but it's kind of interesting and I understand it, and what he calls bizarro mistakes, which are those that no human you've ever encountered has made before or would make again. Okay? As I said, generally there's a reason for breakdowns, and our behavior, while not perfect, is generally sensible, and we surely would like this for our AI systems. And as a result, this is clearly a critical gap. Now, as Osama intimated, this is not a new problem, but it's still very much in search of a solution. So if we want to give common sense to an AI system, I think we have to sit down and ask ourselves, well, what is it? Right? If you ask a dozen people, you're probably going to get a dozen different impressions of what common sense is. Over the centuries, there's lots of people who have opined about this. It's not a new term. But the opinions you have, some of which are quite colorful, are not usually constructive. They don't really tell us how to build a better AI system. Emerson said, common sense is genius dressed in its working clothes. I'll get back to that in a minute. Somerset Maugham actually said almost the opposite, that common sense is another name for the thoughtlessness of the unthinking. Yi-Jin Choi, I mentioned her earlier, has a very colorful metaphor about common sense, saying that it's the dark matter of intelligence, it's hidden, we don't usually articulate it, but none of these things tell us what exactly you do. If you show me something, is that commonsensical, and how do I get it into a machine? So how is the term used in average everyday use? This is a fun exercise if you'd like it. If you go on Amazon and search for books that have the word common sense or the words common sense in the title, you'll get literally thousands, and they're quite interesting. So for example, you might find The Common Sense Guide to Hand Feeding Baby Birds. You might find The Common Sense Guide to Uncommon Fruits and Vegetables. This is one of my favorites. Dude, What Were You Thinking? The Common Sense Guide to Dating and Relationships. Or The Common Sense Guide to Gardening in the Nude. Finally, one of my favorites, Eat, Sleep, Poop, The Common Sense Guide to Being a First-Year Parent. Now you might ask yourself, these are widely varying bits of subject matter. They're all using the same words. What do they mean? And I think you could argue that kind of the common thread, if you will, is that we're going to tell you a bunch of things to know about some topic, not till you'll become an expert, but to guide your actions in a sensible way in ordinary situations. So maybe you've never encountered baby birds before. This will give you some hints about how not to cause trouble, and they all, at least according to the authors, you'll think of them as commonsensical. Now, again, that's not terribly constructive, but it's interesting to see how broadly used the term is and how little understood it really is, at least from a technical perspective. So what would we say are some of the key characteristics of common sense knowledge? So firstly, most people would agree it's broadly known. You know, you say things like, well, everybody knows that you don't put your hand on a burner to see whether the gas is on, right? Now, it's a little bit of an exaggeration, but by the time you're an adult, there are many, many things that we all share either as humans or maybe as a more local community, because there can be common sense that's a little bit more localized to one community than another. But basically, it's broadly known stuff. It's usually about mundane things. It's not rocket science, and together these two things really contribute to the word common. It's actually ambiguous between common amongst all of us versus about common things, but that's okay, a little sleight of hand, it makes sense. Generally speaking, when people talk about common sense things, to most human adults or those in the right community, things appear obvious. You might have forgotten it, but somebody will remind you, say, oh yeah, of course, that's obvious, right? Why would I go left if the school's getting out? I didn't think of it, but yeah, now that you tell me about it, it takes nothing to realize the consequences of what you've told me. One of my favorite quotes is that Baron de Holbach basically called common sense the judgment to discover plain truths and palpable contradictions. So obvious stuff. It also tends to be simple. You don't get big convoluted descriptions or rationales for things that people think of as commonsensical, right? Bob Marley said he's a common sense man. Basically that means if he explains something to a baby, the baby understands it too. So that's his interpretation of common sense. It's also largely based on what we know and have experienced personally, although commonsensical things can be conveyed from parents to children and in other situations, but an awful lot of it is trial and error as a child. And then you realize, oh, that always happens when I do this. You know, if I push the glass to the edge of the table, it always falls off. Maybe I didn't know that when I first started, but then it becomes sort of commonsensical. And Albert Einstein himself said, common sense is the collection of prejudices acquired by the age 18. Okay? Common sense reasoning is also typically very fast. If you look at that T-intersection example I gave you, it didn't take me a lot of thinking to decide to make a right turn rather than left. Took some, but not much. Typically qualitative, very shallow, but importantly, it does involve a certain amount of cognition. Because if I make the right turn and my wife turns to me and says, why did you do that? I can say, because you just told me the school's letting out and I don't want to deal with the crowd of vehicles in front of the school. It's also, importantly, reasonable and making generally appropriate conclusions. That is, it's roughly speaking logical. Not necessarily purely deductively logical, but it's definitely speaking logical. And in fact, we wouldn't use the word sense and common sense unless we kind of implied that. So commonsensical things are typically rational and at least semi-logical. And perhaps above all else, it's really practical. It helps us get along every day in virtually everything we do. In fact, I would argue that if you try to carve up the things that you know and how you use them, commonsensical things completely predominate during the course of an average day. Now, what types of knowledge are common sense knowledge? This should be pretty easy and obvious. At least it's easy to make distinctions between extreme examples. So for example, something as mundane, sort of the dark matter of intelligence that we all know, we never articulate. Once you're dead, you stay dead, okay? Probably need to learn that as a kid, but once you do, it's considered commonsensical. On the other hand, something about CYP450 enzyme polymorphisms typically could be argued as not commonsensical. So there's clearly a divide between what people often think of as expert knowledge, which has details, technical domain, often involves special education, and average everyday things that all children learn as they get around in the world. Now, as I mentioned, the idea of common sense being important in AI is not a new idea. And in fact, there's been some really interesting work that's continued to go on for a long time in the field. The prevalent view, though, I would argue, is that common sense is mainly about potentially very large numbers of accumulated facts and rules. When you think about how many commonsensical things you know when you start to write them down, it's a very, very long list. And one of the problems in the early days, I don't know if you're familiar with the expert systems world back in the 80s, but AI had a big wave of interest and investment and excitement when it was starting to duplicate through what were typically rule-based systems what human experts could do with things like infectious disease diagnosis, mineral exploration, factory floor configuration of products, and things like that. But people found these systems would break down in very odd situations because, as some of the pioneers pointed out, they were missing these little glue facts that we all know but we never articulate, and we never extracted from the brains of the experts when we were writing down the rules. So some of this work started back in the early 80s, maybe even late 70s. A lot of it was generated by a guy named Douglas Lenat, who in a minute I'll show you what he started. But a lot of people who were coming out of the expert system tradition realized that these things were not very robust. Now, in addition to common sense facts, lots and lots of things like once you're dead, you stay dead, or don't put your hand over an open flame to see if the gas is on. We need a certain amount of inference because you have to connect the dots, so to speak. And that's both between commonsensical things we know and common sense and more expert things. And there's a part of the field, Osama mentioned the term, that generally speaking, been called common sense reasoning. And that's never really coalesced into a really cohesive kind of formal research domain. A lot of it's kind of hand-wavy, or people were writing software systems that exhibited this, but there's sort of a flavor of it that are things that are typically more qualitative, have a heavy dose of causal reasoning, and look at things as more plausible conclusions rather than purely deductive conclusions. So AI's view over the last 60 years of common sense has generally been to focus on very large common sense knowledge bases with a little bit of inference. So the project that Lenat started, called Psych, was actually started back in 1984 and continues even to this day. It was a remarkable tour de force of persistence. Sadly, Doug passed away just a couple of months ago, but I think his legacy is continuing. And the numbers, if you look at the Psych website, they'll show you some very, very, very large numbers of concepts and rules and inference methods, actually, that were all constructed by hand. He hired basically armies of knowledge engineers, and the company persisted for almost 40 years. And so there are 25 million axioms that are actually embedded in the system. When you turn on inference, that gives you hundreds of thousands, if not more, 1.5 million or more concepts. So this is a huge endeavor of common sense knowledge. Now, on the flip side, even though this has not been approached this way, you can argue that LLMs trained from huge amounts of internet available data also encode in a certain way a certain amount of common sense knowledge. They weren't intended to do that per se, but you can ask these things, especially when you get to ChatGPT-4 and some of the recent versions of Gemini and Claude, et cetera. You can get some pretty reasonable common sense conclusions to your questions. There's a way in which the Psych project was your classical, good old-fashioned AI, logical axioms and deductive reasoning methods, and completely data-trained large language models, very different ends of the spectrum, were all after sort of breadth of knowledge so that systems could be more robust when they were doing what they were supposed to do. Okay? The thing that is a challenge with these things, as good as they are, and I think this holds equally for the logic versions and the language model versions, is that they're largely what you might call transactional, right? As I mentioned, there's a focus on very large knowledge repositories. You can go beyond the explicit facts with inference regimes. Psych, as I've implied, has many, many, many inference methods. But These systems work by and large as what you might think of as a fact calculator. Imagine you had a new kind of calculator that had the large psych knowledge base in it, but you put in a few new axioms or sentences, or you do it with a natural language sentence in a language model, and you ask it a question and you push the button and say infer, and out comes your answer. And that's the end. Now, sometimes you can have an ongoing multi-step sequence, but basically they're very transactional devices. I imagine that most, if not all of you, have used ChatGPT, and you can have a sequence of things that you can talk to it about, but when you start it up again the next time, it doesn't remember what you did the first time, and there's no telling whether it'll give you the same answer the second time you try it. But nevertheless, these things feel like localized, novel versions of calculators. Now, they can do really impressive things. I have to admit, a few years ago, Doug wrote a really interesting article called What AI Can Learn from Romeo and Juliet, and he talked about a pretty complicated question that involved many, many steps of common sense inference to answer it correctly. So the question was, when she takes the feigned death potion, does Juliet believe Romeo will believe she's alive during the time she's in suspension? Hopefully you remember the plot of Romeo and Juliet. You know that she's taken this potion that doesn't actually kill her, but looks like she's dead, and Romeo comes and he's supposed to know, she hopes, he was supposed to be informed that she's actually not dead, okay? Well, to answer this question takes quite a few inference steps and a whole lot of common sense knowledge. And in this paper, Doug articulates all the steps, and this is a pretty challenging, pretty hairy inference problem, and Psych does it well. But again, it was set up, and then he asked one question, and that's the end of the story. Good common sense reasoning inside of it, pretty impressive when you look under the hood, but just kind of local and transactional. You can do a similar thing, of course, with ChatGPT. I asked it the same kind of question about Romeo and Juliet. I didn't have to feed it the plot of Romeo and Juliet, which Doug did for Psych, because it's seen it somewhere before. But nevertheless, it gives a pretty plausible answer. It doesn't give me a simple yes or no answer like Psych did, which is a little bit annoying, but perhaps I could have prompted it to say, just give me a yes or no. But as we all know, these language models fabricate answers, or what people loosely call hallucination. I don't really love that term because it's very anthropomorphic. They basically make up stuff. And it's unpredictable what they make up. Sometimes it looks plausible, but it's just wrong. And neither Psych nor ChatGPT, in some sense, do anything in the world. They're just local calculator boxes. Very elaborate, very impressive. I'll say a few words about this at the end of the talk, but nevertheless, by and large, think of them as very large, novel fact calculators. So a crucial point I want to make here, and this may be the most important slide in the deck, is that common sense is not just about knowing all of these facts. Life is not a gigantic commonsensical Jeopardy game where you just give an answer or question to an answer, so to speak, and then you move on to something completely different. It's about the appropriate and timely use of all those things in the right setting. That is, the argument here is that common sense, to say that something has common sense, any one of us or a machine, I think we need to go far beyond the statement that we know an awful lot of common sense facts and rules. So we might arguably say that common sense is the ability to make effective use of ordinary, everyday experiential knowledge, that's sort of the common part, in achieving ordinary practical goals. Now, interestingly, Robert Sternberg, who's a psychologist, has a team of folks he works with who have actually defined common sense as practical intelligence. And he and his team contrast that with other types of intelligence. But nevertheless, it's interesting that this aligns very well with some psychologists have said. Now, to pursue this just a moment further, remember I said that Emerson said that common sense is genius dressed in its working clothes? At first I thought that was just poetic, but when I thought about it a little bit more, it really does make sense that all of that stuff you know needs to be put to work in order for you to actually have and use common sense in the real world. Here's some simple examples, right? We all know, I should assume, that driving drunk is both dangerous and illegal. common sense fact, if you will. Well, why do so many people do it, right? So there's a difference between knowing it and putting it into practice, especially at the appropriate time. We know things that on the face of it are contradictory. Haste makes waste versus he who hesitates is lost, sort of commonsensical things. They're in direct opposition to one another. Or sometimes our reptile brains override our common sense guardrails. In New York City, you will see signs on subway platforms that basically say, do not jump down on the tracks to retrieve your dropped cell phone. Now, normally, why would you have to tell somebody that? Okay? Jerry Seinfeld, in one of his routine once, said that he found in a store a Superman costume that had a tag inside that says, do not attempt to use this to fly. Now, anyone with common sense, you wouldn't need such a warning, but it doesn't always come into play in everyday life, and that's really the crux of the issue here with AI. Even if systems know a zillion common sense things, they have to use them at the right time. In fact, I asked ChatGPT to tell me what about the contradiction between haste makes waste and he who hesitates is lost, and it basically gave sort of a sage answer, which is the key is to find the appropriate timing and approach for each situation, recognizing when to act swiftly and when to proceed with caution. The irony, of course, is it told me that was just the right answer, but it doesn't know how to do that itself. So let me give another very quick example, kind of along the lines I've given before, and then give you a couple of sort of conclusions before we wrap up. So imagine you're on a mission across town to get to a grocery store to pick up something for a barbecue. So you're here in this car, and you can imagine this is a self-driving car someday, not right now, but someday, that wants to get to Jones's Grocery, and you're sitting and the traffic light in front of you does not change from red to green. And you're patient, you sit there for a few minutes and more minutes and more minutes, and at some point, it's clearly indicative of something strange going on. Okay, now for the sake of argument, assume that you've never run into this situation, because if you have, you'd probably have a ready-made stock of workarounds or some quick decisions. But imagine you're trying to figure this out, okay? And you hear to the far right a bunch of music, and that triggers in the back of your head that you remember it's Independence Day, okay? So something quickly clicks and you say, okay, there's a parade probably coming down the street in front of me, and there might be a policeman somewhere I can't see. He's keeping the light red. So what do? Well, I've got some alternate destinations that might provide me the same groceries, maybe not as high quality as Jones's, or I could just wrap up and go home. So a lot of questions come to mind. And each of these questions could probably be answered piecemeal by Psych or ChatGPT in this kind of transitional calculator mode. So can I safely get across this intersection anyway, even though it's a red light? I don't know whether my Tesla will do that right now because it completely violates a law, and there might be black and white on that. But believe me, if you live in New Jersey like I do, it happens all the time. Okay? Are there other places I could go to that could help me satisfy my goal that would help me avoid this troublesome intersection? Can I make a U-turn here? Can I physically do it? Is there a barrier in the street? Can I do it legally? Can I at least do it safely? How do I do it? How about a typical New Jersey maneuver where I make a right turn on red, I go halfway down the street to make a U-turn, and then I make a right turn, and I continue on the street that I wanted to get on without literally crossing the traffic light impaired intersection? I might ask myself, how badly do I need this thing? Will the picnic sort of fail if I don't get this item? Or is there another place I can get it, or can I just do this later? So here's the thing. I use common sense to deal with this situation. A lot's going to depend on the situation itself. Are there other cars around? Are there pedestrians? Is the quality of food at this place much better than that food? Do I just want to give up and go home and try again later? Even recognizing that it's a parade. Each one of these is sort of a common sense inference, but I need to put all of that to use to be effective in getting me to achieve my goal. Right? And again, this is something that you're typically not going to get with Psych unless there's a lot of hand-holding in an ad hoc way by the user. Now, let's dig a little deeper into common sense. Given we have a general sense of what it is, these sort of obvious, quick, qualitative inference things that really have to be put to use in practice to match the situation, what is it really for, and when in cognition does it come into play? Now, that's not to say if you're building an artificial cognitive system, you would do it to exactly mirror what humans do, but that's a pretty good set of inspirations, and we can see where humans have been successful or unsuccessful. It's generally supportive of, as we can see from these examples, rapid decision making in mundane, everyday situations, short-circuiting the need for resource-intensive analysis and reflection. If every time I ran into a slight issue, like the door was locked here when we came to this room, do I have to sit back and start calculating, or do I know the person to ask? Or if somebody simply tells me the combination, I know what to do. It's used based on common experiences for, as I've said, quick qualitative decisions. It's very fast. When I was at that T intersection, I didn't sit there for 5 minutes trying to figure out what to do. But most importantly, it's got an element that we might call cognitive penetrability. It can be affected by being introduced to new beliefs and observations. That is, my decision can be impacted by things that I learn and things that I know. It's not just a reflex, right? It's not an impenetrable reflex. So if somebody in the seat to me says, it's 2:30 and the elementary school is letting out, that can change my decision. Okay, so common sense lies somewhere between what you might call routine behavior, which is the kind of stuff we do all the time, almost all day, and much deeper, more thoughtful analysis. And it also, this reflects kind of what I implied before, the importance of expectations about what's going to happen when I try to do something and the goals that I'm trying to achieve. Now, common sense also appears to work in cognition, at least in two different directions. So it's active from the bottom up, because if you think about it, even if you're not, ironically, thinking about what you're doing, like you're trying to come into this conference room and find a seat, there's something going on in the background, it might be passive, that has expectations about what you'll find in the conference room. So if you walk in the door here and the chairs are roughly ordered and the crowd is starting to gather, you don't think twice about it. You don't even do anything, you don't even realize it. However, if your expectations of a talk in a conference room are not met, you might react. So if the chairs in here were all upside down, or if there were no chairs at all, you might notice that and then do something about it. So there's kind of an ongoing, constant recognition with expectations. Now, when you walked into this room, you weren't thinking about getting through security at the airport, right? You wouldn't expect to see TSA people and metal detectors in here, right? So that stuff is out of mind, but when you come into a room, a set of a frame, if you will, of expectations somehow becomes active, but not necessarily conscious. And typically, it's much easier to apply common sense when you're running into familiar situations. Now, way back in the 1970s, there was some really interesting work that sort of fizzled out after a while by Marvin Minsky and colleagues at MIT and Roger Schenck and colleagues at Yale and Northwestern around things they called frames and scripts, which were sort of prototypical patterns that gave you expectations when you walked into a situation and told you what to do in such a low-key way that you don't even have to think about them, right? You walk into a doctor's office, you've never been in this office before, the first thing you're going to do is maybe find the receptionist's desk. Well, you've never literally been in this place, but you have expectations. Likely there's a glass wall. There might be a hole where you can speak to someone. Maybe there's a sign that says, official authorized personnel only, and those expectations are met and they tell you what to do next. Very commonsensical. And the other thing it does in this bottom-up way is it helps you detect anomalous situations so that you can pull into play more thoughtful analysis or evasion of danger if something looks like it's very strange. Now, common sense also helps us from the top down when we're putting together these plans like going to the grocery store, generally pretty mundane. We use common sense facts and basic knowledge we've had before and expectations to generate the plans, and as I've mentioned before, a very critical element of this is an intuitive sense of causality. Pre-structured everyday plans, like what do I do when I get inside the doctor's office? can have sort of contingencies built in them. I'm doing it kind of a rote fashion, but if there's no receptionist window, I may look for something that's the equivalent, or I may look to the right and nothing there, I may go to the left. So I can sort of execute these sort of robot plans in a way that actually has interesting decisions and actions, but they're very shallow, very commonsensical. And then if something goes wrong, I can invoke much more thoughtful planning, right? So in that traffic light example, I might have to sit back and start thinking about better routes to the grocery store or things that I want to do instead. And these two types of process interact. They're not completely separate. Bottom-up use of common sense actually is always active and can really affect the top-down execution of a plan. So if we want to put this all together, I'm not going to go over this in detail, but if you start to think about what should be the architecture of a system that uses common sense to get along successfully in everyday life, you don't just have a giant baseline common sense knowledge base like psych. You have a lot of surrounding processes that help you use it in the right way at the right time. So you might have a plan execution component, and you might have a watcher component that's always following what you're doing and not raising a flag unless an expectation has failed. Now, in addition to that, I don't have a good account for it here, but language is a very special element that we would need to work into this because it's two-way, and as I mentioned before, you can learn things through language that can affect your behavior that are maybe different than what you're seeing with your eyes or feeling with your hands. Now, before I wrap up, some of you might have recognized some of this about related to what has generally been referred to as the difference between System 1 and System 2. How many of you have read Kahneman's book? Not too many. Well, maybe you're familiar with the distinction. The idea is that System 1 is a rapid, almost reflexive, kind of intuitive component that doesn't do deep reasoning and isn't really analytical, and that's contrasted with System 2, which is a more thoughtful back end that allows you to do rational reconstruction and thought and planning. And the thing is, this distinction, which everybody talks about these days, even in AI, it's not fine-grained enough to handle this common sense element. Common sense, as we've said, is quick, right? You come to that T intersection, you can quickly decide I'm going to go right instead of left. I want to turn off the stove because the pot's boiling. It doesn't take a lot of time, right? But it's, as I've called it earlier, cognitively penetrable. It depends on beliefs, and if those beliefs are changed, your behavior might change. That's more of what Kahneman called a System 2 activity. So in our estimation, the distinction is not enough. And interestingly enough, Kahneman doesn't even mention the words common sense in his book, which is a little bit surprising. But another way to think of it is this is sort of a different cut, an orthogonal cut to cognition than the rapidity versus analytic processing that Kahneman and others talk about with System 1 and System 2. Okay, let me wrap up with one or two quick conclusions. We've all talked a lot about interpretability, explainability in AI. It's a popular topic these days. I think it's fair to say, you hopefully agree with me, that when systems are autonomous out in the world, they are going to have to be responsible for their actions. Okay? If they're completely cut off from any human oversight, then if there's any responsibility at all, it's got to be on the autonomous system itself. Like people, as I've said all along, autonomous AI systems need to have good reasons for what they're doing, and they should be understandable. We may not agree with them, but at least they should be discussable and maybe changeable if necessary. And if an autonomous system ever has to be taken to court, it's not going to fly to give the jury a set of 200,000 weights and say, that's why I did it. Okay? Now, I don't know if you've heard of Daniel Dennett, a very important philosopher who's had a lot to do with AI. Unfortunately, he passed away very recently as well. He created a point of view he called the intentional stance, which basically implies looking at a system that does certain activities as doing things because it has goals and operates on a set of beliefs. So if a system is an agent, if you will, we often think of this, certainly with people, and I think we begin to think of this with AI systems, that the agents did things because it believed some proposition P and wanted to achieve some goal G. And I think one could argue that if we're going to take complex AI systems like we've already started to develop and have them be understandable at all, it's going to be in these intentional terms. Whether a system actually has an identifiable node in a graph that's a belief, separate question, but we're going to impute to it a set of beliefs and a set of goals, and that's how we're going to think about the reasons it did things. And I would argue that, given all we've said today about common sense and how common it is amongst people, it's likely the best foundation for thinking about intelligible intentions in large AI systems. Finally, I think a really critical point is that common sense is a pretty significant ingredient, in helping AI systems be redirected to do the right thing when they take mistakes or to avoid mistakes in the first place. And this goes back to this point I called cognitive penetrability. By the way, that's not my term. I think Zenon Polishin, cognitive scientist, invented that term. But basically, deployed AI systems need to be capable of changing when someone they're working with disagrees with their reasons. And if, let's say, we're having a conversation either as a peer or as a supervisor, if we see that the system has a belief that we think is false, we should be able to explain an alternative belief, and the system ought to be able to adopt the new belief and change its action based on it. If I didn't think school was going to let out in the next hour and my spouse tells me it is, I need to be able to update my belief and take action based on it. So the architecture of an AI system, not just a giant common sense knowledge base, but a full-fledged cognitive system, needs to be possible, needs to make it possible for me to isolate a belief, potentially a mistaken belief or a goal, and have it changed. Now, that doesn't mean I go in and I flip a bit from positive to negative, but argumentation ought to work to help change the beliefs of a cognitive system. And this kind of generally favors the thinking about symbolic knowledge in the back end of these systems. Now, there's a caveat here. In my earlier days, I would have insisted very strongly that there are formal symbols in there and you can actually find propositions. I think with LLMs and the like, you're not going to find those, but maybe you can identify sets of nodes, sets of weights, or meta nodes that actually show you identifiable beliefs that can be changed. And I think this really is really crucial. I don't know if you've ever been in a car with so-called self-driving technology, but when it makes a mistake, the first thing you want to do is yell at it and say, don't change lanes now because of that slow truck over there. Or, look out, that's a pedestrian, put on the brakes. Can't do that, right? Couldn't even do it in any formal language or any other way of interacting, but you certainly can't do it at the level of beliefs and goals and instructions. So our belief is that bolted on after the fact explanations, which is sometimes part of what people call explainable AI, is not adequate because those beliefs that you're trying to explain post facto do not actually influence the behavior of the system, okay? And all of this takes us back to the very beginning of the field in an interesting way. As far back as 1958, John McCarthy wrote a very famous paper, which notably in the title had the words common sense. And the major research path he wanted to set the field on was building what he called an advice taker, a system that could take naturally expressed beliefs, changes of goals, situations being described, and actually have the system adopt those beliefs and change its behavior. And here we are 65, 66 years later, and we still don't have it. So my conclusion is we really need to get back to this. As I've said, acting commonsensically overall is more than knowing even millions of common sense things. Common sense beliefs and goals, as I've said, should support explainability and instructability or advice taking. And I think really, when you think about it, autonomous systems should not be let loose on the world without common sense. They won't be able to stop themselves when they're about to do something silly, or correct themselves when they've just done something silly. So if Alexa had said, put a penny on that set of prongs, and something had triggered a thought in its head, and it said, wait a second, I changed my mind, don't do that, that would be sort of an application of common sense, which would still be very valuable, even if it wasn't done before the act was taken. So I would love to see our work on very large-scale knowledge bases and LLMs augmented to deal not only with common sense facts and rules, but the use of this in everyday situations kind of along the lines that I've described today. And hopefully you've picked up the sense that the overall architecture of the system, when the common sense knowledge is used, when reasoning is done, how it's used top down and bottom up, all of that really matters, and we've generally speaking been ignoring it in the recent past of the field. And this has now taken on a really significant urgency, because you're probably aware, AI is moving now from chatbots to what some people call agentified LLMs. LLMs and other AI systems can actually take action in the world, from factory floors to chem labs. OpenAI is working on this. You've heard of Microsoft Copilot. So now these things are getting out there and doing things which could have significant effects, hopefully not necessarily dangerous ones, but they could. And one of the interesting things, I mentioned the article in the Times this morning about this new Meta AI tool, and there was an article just the other day that says, you can't turn it off. There's something wrong when we let loose autonomous and semi-autonomous systems that don't have common sense, and we can't stop them. So keep that in mind. If you'd like to read a little bit more on the subject, Hector and I have written a book a couple of years ago. There's a number of articles out there, and I'd be very happy to share some further thoughts with you later. And with that, I want to thank you all for your attention.
Okay, so we have enough time for one in-person question and one online question. So does anyone have a question for Ron? By the way, thank you, Ron.
My pleasure, thank you.
I do have a question. Might be a bit, can I ask? Yeah, well, thank you for the presentation, first of all. I'm going to bring up Marshall McLuhan here, who used to say that in communication, context is everything. If you don't have a context in communication, it doesn't matter, you know, the emitter, the receiver, the noise in between. Without a context, there can't be a proper understanding, right? And it's something that I learned when I did my first martial arts class. I know it's common sense to not get punched in the face, but nevertheless, I got punched in the face because I had to learn that by acquiring muscle memory, right? Because I am embodied, right? That's an embodied experience. So I think one of the limitations of LLMs that you brought up quite a few times is that they're not yet embedded or embodied, right? They don't experience the world in an embodied fashion.
Right.
So that might be a limitation to their common sense development, I guess, and also the fact that I think machines cannot, to my understanding, and it might be limited because I'm not an expert of AI, but they can't manage semantics very well. Syntax, yes, but if, like the red, they understand the code, but what red is, they don't really understand the abstraction, like the abstract concept. So does that mean that we can never have common sense in AI? Or maybe is it a good thing that they cannot deploy common sense because maybe they need humans to be kept in check? Kind of thing, I don't know.
I'm sorry, Ron, before you answer, do you mind just kind of summarizing the question just for those who are online?
So let's say the gist of it talks about the fact that the systems that we've been talking about here and most AI systems right now that are out there that people are talking about are not embodied. They're not experiencing the world and interacting sort of in a face-to-face, direct, sensory way with the world. Although I'd argue that's not true for self-driving cars. Their interaction with the world is limited, but nevertheless, sort of the rubber meets the road, so to speak. But nevertheless, I do agree with you and believe that it's really important down the line at some point to take these disembodied intellects that we're building in language models or large knowledge bases and get them into some kinds of physical systems and start to connect the symbolic knowledge that's inside them with the real world. There's a problem, you may have heard this, called the symbol grounding problem, right? Which has to do with the fact that machines do a great job of acting as if they understand red and love and hate and other sensory concepts, but it's hard to believe they really understand in a true way because they're not out there in the world physically experiencing it. And I think we're going to see us get to that eventually. It's going to be very important. There's still an awful lot you would want these disembodied systems to do that reflect what we think of as common sense. So if you look at the example, the Alexa example, and there are many, many, that could do some real harm without a body, right? You could argue Alexa has a microphone and it's listening, but, right? And if it didn't think about common sense where, gee, somebody could get electrocuted, or a 10-year-old child might take me at my word as opposed to doubting what I'm asking it, which is another sort of commonsensical thing. Harm can be done and problems will happen. So I still think this is very relevant right now, even where there are no embodied systems. But I think in the long run, AI is going to be richer and more interesting to study as a whole when these things are now put into some kind of embodiment in the world, and largely they move around and have some kind of sensory experience.
Thank you.
Thank you. So we are at time, but I do want to ask one last question.
Sure.
This one is online. It is, can common sense be learned by feeding the dataset pairs to LLMs, or can it only be achieved by a system consisting of LLMs and rule-based systems?
I assume everyone heard that, or?
Yeah, if you don't mind repeating.
No, because
So
he's way over there.
The question was, can common sense be learned, or can it only be achieved by combining, say, LLM-style machine learning-based systems and more symbolic reasoning or rule-based systems? And I'm going to disappoint the questioner because I don't know in the long run what the best way is to build these things. My own inclination, I have a research strategy I would carry out to try, and I would start doing just what you think, which is use, I don't want to rebuild Chat, or GPT-4 or Claude or any of those systems. A tremendous amount of time and energy has gone into them, or Psych. I would use those, but I would really want to put them in this integrated context so that beliefs in the more rule-based component, which might be the ones I would converse with when I'm trying to get it to change its beliefs and goals, could impact what's going on in the neural net. And I don't know exactly personally how to do that, but I would sort of look at a hybrid approach and see if I could make it work. And then the original part of the question, in some sense, maybe this is trivial, common sense is learned, because I don't think we're born with, the belief that once you're dead, you stay dead, or you don't put your hand over a flame. Kids sometimes learn that the hard way. So clearly learning happens. The question is, what kind of learning is it? Is it just an infinite dimensional space of weights moving around a network, or are there conceptual things that arise from learning that we can then reflect on and discuss with others and use as justifications for actions? And that's the place I'd really like to see some emergent new work happening, where machine learning is used, but generalizations, concepts, rules are at least present in the language model, where you can discuss with them and the machine can use it for justification. As I kind of implied, I'm waiting to see the first case where an autonomous AI system does something wrong and is called in front of a human jury, and it has to defend its actions. And there's no machinery right now to do that in any kind of a comprehensible way. So thank you for the question.